Today I will present code, controllable federated prompt learning at test time. The central problem is deployment. After federated prompt training, each client may encounter new domains, corruptions, or out-of-client data. We want to adapt with only unlabeled target data, while preserving the global knowledge learned across clients. Figure 1 shows the progression. FPL learns a global prompt, which captures shared knowledge, but is not tailored to each client. PFPL adds local prompts and improves personalization before deployment. However, both are mostly static once deployed. In real applications, client data can shift after training. This creates the need for TTFPL, test-time federated prompt learning using unlabeled deployment data. TTFPL has two challenges. First, adaptation must be unsupervised, with no labels, no training samples, and no new communication. Second, the update should not overfit to the current target batch and destroy global semantics. Code addresses this using three prompts. The frozen clip prompt as a domain-neutral prior, the global prompt for shared semantics, and the local prompt for client-specific patterns. The key idea is to select among them dynamically. Figure 2 gives the full pipeline. Code first uses clip-style image text matching to predict pseudo-labels on target data. Then it analyzes the predicted label distribution with model and computes an alignment signal. This signal tells us whether the current data looks globally aligned or locally skewed. Finally, samples are split by confidence. High-confidence samples use pseudo-label refinement, while low-confidence samples use conservative sample-wise prompt tuning with augmented views. Model stands for model data alignment. It combines three statistics from the pseudo-label distribution. Gini captures dominance by major classes. Entropy measures global dispersion across the label space. Regularity measures balance within the active predictive classes. These are combined into a unified score, then compared with the client-specific ideal reference to produce psi. Positive psi favors general or global behavior, while negative psi favors stronger local specialization. The adaptation rule is controlled by both confidence and psi. For high-confidence samples, pseudo-labels are reliable, so code updates a selected prompt with supervised style loss. The global prompt when psi is positive, and the local prompt when psi is negative. For low-confidence samples, pseudo-labels are risky. Code instead uses augmented views and entropy-based tuning, initialized from the clip prompt or local prompt according to psi. This reduces noisy over-adaptation. The results show that code improves robustness across 5 benchmarks. On CVPR 100, it reaches 71.08% average accuracy. On ImagineNet, it reaches 81.44%. The strongest gains appear under out-of-client shifts, where personalization alone often fails. For example, CVPR 100 Duke improves to 40.34%, compared with 19.24 for TPT. ImagineNet Duke improves to 36.60%, compared with 6.87. Food 101 Duke also rises to 58.50%. These results support the tri-prompt controllable design. The evaluations confirm both components. Model works better than using only Gini, entropy, or regularity, because it combines global coverage with local stability. The confidence partition is also important. Removing it hurts especially on out-of-client and mixed shifts. In summary, code introduces TTFPL as a deployment time problem, and shows the prompt adaptation should be data-aware and controllable. Adapt after deployment, but choose carefully which prompt to trust.